Okay, so we're back with question 5, right? So, yeah, so I'll take some time to go through the principles as well, and not just the answer. So let's talk about it. So in this question, we're given an inductor, right? And there's a DC power supply that pushing current through the inductor, and we know from our from our lessons on inductors that inductors, they don't like current going through it. So the inductor is not going to instantaneously, when you apply a DC voltage to the inductor, right, it's not going to immediately jump to that current value, right? And instead, it's going to rise. So yeah, it's going to slowly rise like that, and this comes from solving the differential equation. So yeah, and in fact, in the long run, if you don't have a resistor here, right, then your inductor actually goes to infinite current, because inductors, they short DC, right? But if we do have a resistor over there, then we know that it's going to asymptote towards your E over R, right? When essentially asymptoting towards when the asymptotically approaching the system, a state where your inductor is essentially a short circuit. So yeah, anyway, for this axis is current I. Okay, so what we're told is that the current is increased until it reaches a steady state. So yeah, so until it reaches the final steady state. Okay, so over here they're saying that there is some steady state. So I'm assuming that the variable DC supply has some internal resistance that prevents it from supplying infinite current. So we are seeing a scenario like this on the right, right? We are seeing a scenario like this on the right. Okay, so yeah, that's just that. Okay, I can scroll like this. Okay, that's great. Okay, so yeah, so in this case, but instead of having E over R over here, it approaches I of F, where F is the final steady state. So no resistor, but we know our current approaches a final steady state. So by considering the change in energy, change in current, and the energy required to increase the current to its final value, calculate the total energy in the inductor. So the point here is that when we supply current in this circuit, right, because there's no resistive element that dissipates the energy, all the energy that's supplied, all the work that is done by the DC supply, right, must be equals to the energy stored in the inductor. Which I denote by L. So but if we have the function, function I in terms of time, right, then we can integrate. So the energy, the work done by the DC supply, I'll just write it over here. The work done by the DC supply is equals to the integral of the time from time t equals to 0 to time t, right? So work done from time 0 to t seconds is equal to this integral of the current, right, multiplied by the EMF of the DC supply. Now we know the EMF is simply a constant, so we can not worry about that. So yeah, so this is the total work done, and in turn the energy stored in the inductor, right? But now the question is, how do we not figure out this I of t over here? And the answer is that I of t satisfies the differential equation. Right? Satisfies the differential equation. It satisfies a differential equation. And how do we find out this differential equation? We do Kirchhoff's voltage law. So Kirchhoff's voltage law tells you that when you go from, so the current is going in this direction. Let's go in a loop, right, following that direction. So we go here, we jump over here, and that will give us plus E, plus epsilon, right, where the EMF of the DC power supply, because we're assuming this side is the positive side and this side is the negative side. So when you're going from negative to positive, you go by plus E. Then you go over here, and when you go down here, right, is you're going to the EMF is actually yeah, the EMF developed is okay. So first of all, we know that the EMF, the back EMF, right, or the induced EMF of the inductor is minus L di dt. So if the current was increasing, right, then the 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 inductor would create an EMF like this, right, to oppose the change in the current. So when we're going from this side to this side, we're actually going from a higher potential to a lower potential. So yeah, so that's why we minus L di dt. So this sign convention of the inductor, I hope it's clear. So how I go about thinking about this is that I think, okay, first of all, we have I representing the current flowing through the circuit. And what happens when I increases? So what happens when more I is added in this direction? So maybe from 1 ampere to 2 ampere, what happens? If that happens, right, then di dt is positive. Am I right? So when di dt is positive, right, the inductor doesn't like that. So it will develop an EMF that is positive on this side and negative on this side because current is trying to flow from the left to right, right? So it will try to fight back by creating an EMF from the a positive on the left hand side and negative on the right hand side. So whatever other circuit components over here, right, it will see that there's this EMF being generated that's trying to fight back with the DC supply, right? Because you see that now the inductor and the DC supply, they're connected in opposite directions. So then hence, right, when I go from the left to the right, right, I must see a drop in EMF, right, which is why we have this negative sign over here. And at the same time, we also have the inductance over here, meaning that the inductance is how strong the inductor is in opposing this change in current. If the inductor was small, then the EMF induced will be small. Yeah, so as a result, you get this equals to, we've gone one complete loop, so that equals to 0. So yeah, yeah. So this is also known as a lump circuit model, right? If you have been watching Electro Boom, you know that he has started some debate with Professor Walter Lewin, and I respect Professor Walter Lewin a lot. He's the reason I understood electromagnetism in the first place. And they'll be talking about something called the lump circuit model, right? Where they're asking, is the Kirchhoff voltage law does it hold for circuits where the magnetic field is changing? And there's a whole debate about that, but just know that this is known as the lump circuit model, lump element model, right? Lump circuit model, you can search it up, where the Kirchhoff voltage law does hold, even though you have a changing magnetic field, because we are taking into account the changing magnetic field as part of the inductor, right? It's not part of the entire circuit. Okay, so yeah, so yeah, so okay, so we know this is true. So that's one equation that we can work with. Um, so actually, if we go ahead and try, so what if we multiply I on both sides? Then we realize that this is actually equals to, then this is actually just I of t, right? L d I dt. So this is what happens if we bring this part over the right hand side and substitute epsilon into this expression. And I forgot something over here. It's actually dt over here, right? We're integrating with respect to time. Don't forget the integral. Don't forget the differential. Okay, so there's dt over here. And we realize that, hey, there's actually something we can so-called cancel off, but what's actually happening is a change in variables. So physicists will just cancel it off like that and change the limits of integration. But what's actually happening here is a change in variables, right? From 0 to the current at time t, right? And then we have I, right? And then L di. So now instead of calculating the integral from 0 to some time, right? We are calculating the integral from 0 to the current value at that time. And this is a change in variables. I can make a video in changing variable. I can make a video in depth about this integration procedure. And as a result, right, this is if you do the integral, it's simply half Li squared, right, going from I at time t to I at 0, and this is equals to half of Li squared. Yeah. So I is the final so if we now going back to the question, right? If we because if we consider what happens the final steady current, right, when I equals to IF, then we want to find the work done from this to the time where it reaches a steady current, then from 0 to TF, then TF like this is just IF. Like this is just IF. So yeah, so by right, actually this time will be infinity, which is why they didn't mention it in the question. But yeah, so essentially we're taking T to be in TF is actually infinity. Yeah. So in the end, the energy stored in the inductor equals to the work done by the DC power supply from 0 to time TF, where TF is actually infinity, right? And it's equals to this integral. And by using Kirchhoff's voltage law, we're able to express E epsilon in terms of this differential over here. Then we do a change in variables, and as a result, you end up with this thing here. So that's it for question 5. Let's go on to question 6 in the next video.